Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. So, in today's session, I'm going to talk about eigenvalues and eigenvectors of a matrix. So, what are these? You know that if you have any vector and you multiply it by a matrix, this vector will change direction. We can take a very small example. So, let's say I have a matrix 1, 2, 3, 4, just any numbers, and I multiply it by a matrix, say 3 and 4. Okay, meaning this matrix has a slope of 4/3, right? X is 3, Y is 4. So it's have a positive um, slope of magnitude 4/3, right? Now, if you multiply these two, you get the new vectors, right? You get 3 plus 4 is 11, plus 8 is 11, and then 9 plus 16 is 25, and now the slope is much higher. It's 25 over 11, which is much higher than 4/3. So we say um, for many vectors, there exists a matrix. Then when you multiply the matrix by that particular vector, it gives you a multiple of the vector, meaning it makes each direction stable, the same. So basically, that's how we find. So the eigenvector is a vector associated with a matrix such that when you multiply the matrix by that vector, it is parallel to the same vector. Okay? Not only that, for example, if I have a matrix here, suppose I have another matrix that if I multiply by 3 and 4, I get multiple of 3 of 4 and 4s. I may get, say, -6 and -8. I may get 30 and 40. I can get, 17 and a half and 20, meaning the ratio stays the same, meaning the direction is the same. How many of this vector it is? So for example, if I get 15 and 20, meaning this is multiplied by 5, it's like 5, 3, and 4. That would be the eigenvalue of that eigenvector. Again, so to recap, for many uh, for many vectors, there exists a matrix, or you can say for any not for any matrix, for many matrices, there exists a vector called the eigenvector that if you multiply that matrix by that vector, it just stretches it, or it shrinks it, or changes its direction, but keeps the direction, or the sense of the direction will change, but the direction itself stays the same. Okay? So how do we find these? Let's take a very small example. So let's say I have a matrix A. So if you, by the way, if you want to write it, you can say A. If you multiply it by a matrix X, you get lambda times X. Here, A is this matrix. X is the vector. So you get the same vector, but it's multiplied by a constant, meaning it's stretched or shrinks. And it may change sense if you get negative, right? Okay, so let's take an example, and see how we find them. Find these eigenvalues and eigenvectors. Sometimes, they are imaginary. In this case, it changes. There would be a rotation, but that's another story. So let's say I have a matrix A equals 2, -1, -6, and 1. So in order to find the eigenvalues, we do this operation. We say lambda, which by the way is the eigenvalue, multiplied by I, Why by I? Because I want to make a diagonal, I'm sorry, and yeah, I want to make a diagonal matrix that is basically having ones in the main along the main diagonal and zero elsewhere. And since this is a 2 by 2, then this is, of course, is I2 minus A. I create this matrix, lambda I minus A, take the determinant of that and equate it to 0 and solve. That will give me the lambdas. So let's say how we do that. Here is the determinant. Notice you can say lambda I minus A or A minus lambda I. I prefer to say lambda I minus A, but you can also say, this is usually what you will see, A minus lambda I, because that doesn't change the entries of A. Instead of keep changing them and you may forget. So let's follow the same, the convention, even though I prefer that, but it doesn't matter. So I say 2 minus lambda and 1 minus lambda. And here, these stay the same, -1 and -6. Why? Because my I was 1, 1, 0, 0. So when I multiplied it by lambda, it became lambda 0, 0, lambda. And when you subtract it from A, you subtract lambda, lambda. And here you don't subtract anything. And then you equate that to 0. That's a very simple quadratic equation because the size of the matrix is 2. So when you multiply that, notice that multiplying 2 minus lambda by 1 minus lambda is the same as multiplying lambda minus 2 by lambda minus 1. If it's easier for you, that's why I use usually this method to become easy for you. But now you can multiply negative lambda by negative lambda, you get lambda square. You get 2 times negative lambda and 1 minus times negative lambda, you get -3 lambda. And then you get 2 times 1 is 2 minus -6 times -1, which is +6. So you get 2 minus 6 is -4 equals 0. Very simple quadratic equation. You want to find two numbers that multiply to -4, meaning one is positive, one is negative, and they add up to -3, meaning the larger of these two numbers is negative. So of course, you get lambda minus 4 times lambda plus 1. So either lambda equals -1 or lambda equals 4. It means there exists two eigenvectors. If I multiply this matrix by one of them, it will change sense of the vector. So if the vector was 3, 4, it will become, -3, 4 or 3, -4. And if I multiply it with by the other lambda eigenvectors, I will get 4 times the matrix or 4 times the vector, meaning it's stretched by a factor of 4. But how do we find these eigenvectors? Well, it seems easy. You say, for example, 4 lambda equals -1. You are going to write the matrix, the original matrix, but after subtracting lambda. Notice subtracting a negative value, meaning adding. So 2 minus -1 is 3. This stays -1. This stays -6. And 1 minus -1 is 2. So when you multiply that by a vector, so let's call it V1 and V2, you get a 0 vector. So what are the values of V1 and V2 that will give you zeros? Very simple multiplication. You say 3 times V1 minus V2 equals 0. Notice that the second equation is the same, meaning if I divide this equation by -2, the -6 becomes 3, and the 2 becomes -1. So this is the equation that I have. And you say, but there are infinite solutions. Yeah, it doesn't matter. It doesn't matter. For example, I can say I'm going to take V1 and see what V2 equals. So here I get V2 equals 3V1. So I can write this vector as 3 times, I'm sorry, V1, and this is 1, and this is 3. V1 and 3V1. Because V2 is 3V1, right? So instead of writing V2, I can write 3V1. So meaning V1 can be anything, but the eigenvector is 1, 3. That is associated with that. Now, let's say for lambda equals 4. 2 minus 4 is -2, -1, -6, and 1 minus 4 is -3. Likewise, if I divide the bottom by 3, I get the top. So it's basically one equation, V1, V2 equals 0, 0. So here I get -2V1 minus V2 equals 0. So V2 equals -2V1. So if I want to write it, I can say V1 is 1, but V2 is -2V1. So these are the vectors that if I multiply my matrix by, I will get that multiple of the vector. Let's do it. So remember, my original matrix was 2, -1, -6, 1. And if I multiply it by that vector, which is 1, 3, what do you think we will get? Let's do it. 2 times 1 is 2, minus 3 is -1. -6 by 1 is -6, plus 3 is -3. Now, this can be written as -1 or just negative. I just wrote the 1 so you see it. So this matrix didn't change direction. It just changed sense. Instead of being pointing up, it's now pointing down with a negative slope, okay? So you see that the -1 is the lambda, and this is the vector. If you multiply the original matrix again by that vector 1 and -2, what you will get is 2 times 1 is 2, and -1 times -2 is +2, so 2 plus 2 is 4. -6 minus 2 is -8. You can see the 4 right here, that if I factor it out, I get 1 and -2. So that vector, when multiplied by this matrix, has been stretched by a factor of 4. And that's basically the eigenvalues and the eigenvectors. We can do it for any, of course, you can do it for 3 by 3. If it's more than that, you need a computer software or something to give you those, but you understand now the meaning of eigenvalues and eigenvectors. There are a couple of things that can allow you to find them without doing all this work, especially for a 2 by 2. Really? Yes. You know the trace of a matrix? The trace of the matrix is the sum of the elements along its main diagonal. 2 plus 1 is 3. So I know that lambda 1 plus lambda 2 equals 3. Okay? Now, the determinant of that matrix, 2 times 1 minus -6 times -1, which is 6. So 2 minus 6 is lambda 1 times lambda 2. So I have 2 lambdas that when I multiply them, I get -4. And if I add them, I get +3. Yes, -4 and +4 and -1. +4 and -1, when you multiply them, you get -4. And when you add them, you get +3, -1, and 4. Multiply these, you get -4, add them up, you get 3. So a quick way you can sometimes find it much quicker by finding the determinant of the matrix. Now, let's take another one, a 3 by 3 matrix, so that we can see how we do it. Or before saying that, I'm sorry. Before saying that, there is an important, maybe we'll stop after that. I don't want to make it a very long session. We can take another session where we can see how do you check if these things are correct. Of course, we know it is correct, right? We already did multiply and we got that. But suppose the numbers were more, complex and whatever, and you wanted to see that really these are the eigenvalues and eigenvectors. So maybe should I use the back or no? I think it's better to use a new page so that you can see that. We say that this matrix A, which is 2, -1, -6, 1, can be represented as a product of 3 matrices. And you will see, why would I make one matrix a product of 3? Isn't that make it harder? No, it makes it much easier for finding functions of matrices that in a maybe today, later, I will prepare a session for that. For example, I tell you, okay, what if I take this matrix and I want to find its square root? What? Can you find the square root of a matrix? Absolutely. Can't you find the square of a matrix? So why not? So why can you find square and cube and fourth power and you cannot find square root or a cube root? It's the same concept, right? Also, I can find the sine or the cosine of this matrix. I can find the natural log or e to that function. I can find the power of function, even if that power is imaginary. I can raise that to I. Or I can take this matrix and raise it to the power of another matrix. That's crazy, right? Or it looks like it, especially if you are new to linear algebra. But this can be written as a matrix called P times a matrix called D times the inverse of matrix P. So what are P, D, and inverse of P? This is the eigenvectors. And these are the eigenvalues. I should use eigen. That's pretty better. And that's the inverse of that. So let's see. So this thing is telling me that this A can get back, we can bring it back as P, which is the eigenvectors. Remember the eigenvectors were 1, 3, 1, -2. 1, 3, 1, -2. The eigenvalues, they have to match. So the eigenvalue of this was -1. And the eigenvalue of this vector was 0, 4. Times the inverse of this. How do I find the inverse of a matrix? Well, 42 by 2 is child's play. First of all, you get a matrix and you divide it by its determinant. How do you find this matrix? Remember when we did some linear algebra in the statics course, we went over, how to invert a 2 by 2 or a 3 by 3 or a generic way to do it. So for a 2 by 2, all what you have to do is to switch the elements along the main diagonal. So 1, -2 becomes -2, 1. It's as simple as that. As for the other two, you leave them where they are. You just change their sign. Notice this method works only if you have a 2 by 2. It doesn't work on a 3 by 3, for example. What do you do with the other 5 elements? I didn't say here. So And then you divide by the determinant. The determinant is -2 minus 3, so it's -5. So that's basically 2/5, 3/5, negative, I'm sorry, 1/5, and -1/5. Let's check. If I multiply the first two matrices, I get -1 plus 0 is -1. 0 plus 4 is 4. -3 plus 0 is -3. And 0 minus 8 is -8. And then you multiply that by 2/5, 1/5, 3/5, and -1/5. Let's see what we get. -1 times 2/5 is -2/5. And 4 times 3 is 12/5. 12/5 minus 2/5 is 10/5 or 2. -1/5 minus 4/5 is -5/5, so it's -1. Notice the first row is the same. -3 times 2 is -6, and -8 times 3 is -24. -6 minus 24 is -30, divided by 5 is -6. And finally, -3/5 plus 8/5. -3 plus 8 is +5, divided by 5, it's 1. Check. And you say, okay, so what does that mean? It means, for example, a quick thing. Suppose they ask you to find a to the 5th. You'd say, okay, that's tedious. I'm going to multiply this matrix by itself 5 times. Of course, it's tedious. But if you have it like that, how would you raise it to the 5th power or to the 100th power? Of course, the 100th power, you cannot do it like that. This is crazy. Okay? Notice that a square, I can write it as this times itself. So times P, D, P inverse. What happens? What happens is that the P and the P inverse, I'm sorry, I wrote it here. Yeah, it is times P times D times P inverse. This is P inverse, right? So when you multiply it by P, it gives you the I, which is the identity matrix. So they cancel each other because multiplying by I is multiplying by 1. In algebra, it stays the same. So you are multiplying the D by itself. And then you have P and P inverse. And then to get a to the 5th, you multiply times P, D, P negative, times P, D, P inverse, and so on. And every time these cancel, and you end up with D cube in this case, or D to the 5th in that case. So you will end up with P times D to the 5th times the inverse of P. And you say, okay, so how do I find P to D to the 5th? It's so easy because that's a diagonal matrix. The eigenvectors, I'm sorry, the eigenvalues will always form a diagonal matrix. So all what you have to do is to square or to cube or to raise this to the power of 5 and you're done. Remember when you were first introduced to matrices, and many of us thought that to square this matrix, I would say 2 squared, -1 squared, -6 squared, 1 squared, and then they told us, no. You multiply the matrix by itself. You don't square. Here, that's the only time you can do that. You can square these 4 numbers or cube them. So basically what to solve this, I would say, here is the P, 1, 3, 1, -2. And the third one, instead of writing as 5th, I'm going to say 1 over 5 times 2, 1, 3, -1. So I don't deal with, fractions. And then I'm going to say -1 to the 5th is -1, 0, 0. 4 to the 5th is like 2 to the 10th is 1024. But we can write it for now 4 to the 5th. And then I'm going to say equals 1/5. I'm going to multiply these two matrices. So I get -1 plus 0 is -1. 0 plus 4 to the 5th is 4 to the 5th. -3 plus 0 is -3. And 0 minus 2, 4 to the 5th is -2 times. It's not 24 to the 5th. I'm sorry. Times 2, 1, 3, -1 equals 1/5 times -2 plus 3 times 4 to the 5th and -1 minus 4 to the 5th, 1 times that. Here you get -6, -6 minus 6 times 4 to the 5th, and here you get -3 plus 2 times 4 to the 5th. Let me check. I just want to make sure I didn't do any errors. Don't give you something wrong. And here you get -3 minus, oh. Yeah, -3 plus 2. So that, if you want, this would be 1/5 times 4 to the 5th, we said 1024. So this is 3072. So this is 3070. This is -1025. 1024 times 6 is 6144. So -6150, if I did it correctly. And this is 2045. I don't know, something like that. And of course, you can divide by 5. It's so easy, you know. When you divide by 5, you can just multiply by 2 and then take away the 0. And since these end up with 0 or 5, so all of them are divisible by 5. It's so easy. So if I say 307 plus 307 is 614. -102 and -102 is -204. That's how quickly you can divide by 5, right? 615 and 615 is 1230, so -1230. 204 and 204 is 408. Now, let's see if we can take a matrix. Notice this, how long can it take you and how many pitfalls can you end up having. So if I go to the matrices, and I already have a 2 by 2 here, but now I'm going to say 2, -1, -6, and 1. And then quit. And then I'm going to take this matrix, matrix A, and raise it to the 5th power and see. Please, I hope I didn't do math error here. I should have used the calculator. 614 -205. Why did I say? Oh, because of course this is 205 and this is 409. I'm sorry, guys. They end up with 5 and I forget to add the 1. I'm sorry. So 307 times 2 is 614. 615 times 2 is -1230. This is 102.5 FM. Right. Okay. So when I multiply it by 2 is -205, not 204. I was hiding this by error because when I multiply by 2, I will take the 0 away. I'm so sorry. This is a dumb mistake. I hope you don't feel bad, but I apologize for that. I shouldn't do this error. Okay, but you can see we can apply many things. We can raise to any power and end up quickly with the answer. It's much easier and less confusing, even though I got confused myself. Okay, I hope that didn't bother you much, this horrible error, but I apologize again for it, and I wish you all the best, and until we meet again, have a nice day. Bye.